Hello everyone. I hope you're all well. Thank you for joining our live stream this weekend. We continue topic of for machine education and machine learning. Last time, Ivan was describing the workflow from Mid-Journey to Grasshopper, and today we're gonna try some machine learning tools inside the Grasshopper. So there are some, as you might know already. So my name is Anton. Thank you for joining us today, and let's start. As you know, it's crucial in architecture to optimize everything, right? If you have crazy parametric stuff, you cannot just go and produce everything in model, because it's gonna cost you like a shit ton of money. And we're using some optimization tools to prevent spending a lot on this. And one of these tools is clusterization. It is a type of machine learning which allows you to group some pieces together by some parameters. So for example, here you see some kind of facade, and it consists of triangles. Initially every triangle on this facade is different from each other. So they're not unitized because the shape is quite complex, and it could be even more complex in this case. And yeah, and to be able to produce it, we will need to organize this facade, every triangle in cluster, and unitize them. So let's say for each cluster we use just one single triangle, one single type of triangles, and that's it. In this way we'll able to produce, let's say, 50 clusters, 50 groups of triangles, which will be much easier to produce if we produce 50 groups instead of like 1 million of individual pieces. Okay, let's learn how to actually do it in Grasshopper. Let's open a new Rhino document. And let's open Grasshopper. So today we're going to use a plugin called Lunchbox. It's not only machine learning tool, but it has its section of it. So you can see there are several neural networks. There is a different kind of classification. We're going to use k-means clustering. Okay, and let us start with creating a shape, an actual shape, right? We could do it like in different ways. For now, let's go with the easiest one and just draw two different curves in a Rhino viewport. I will move them apart like this. The scale in this stage doesn't matter for us. Then once we have these two curves, I will just create a loft between them. Let's say I select both of them. I'll reference them to Grasshopper. And using loft, sorry, another language, this one is good. Using loft, I will create a shape. It doesn't matter how many curves you have, you can create like crazy loft or just simple like this. It will work equally well for both options. Once we have a loft, in my case it's a untrimmed surface. This is good because we have without any problem transferred to mesh. I'm using mesh surface component. To divide it into some rectangles. I want to make them more or less squarish. So just by adjusting the number in U and V directions on the surface. Let's hide everything we don't want to see. Sort of like this. And we've got a mesh. That's great. So for now, this is a squared mesh. And again, we can use clusterization with any kind of facade tile. In this case, we're gonna use triangles, but also we can work with hexagons, squares, and whatever shape you want. Okay, so once we have the squarish grid on the surface, I would like to triangulate it using just simple triangulate component. I'll get my triangles. That's pretty much enough for my facade. I will leave them as it is, as they are. And we'll talk a bit about clusterization, about how it actually works. So for now, let's switch to a new document. In this one, I will create a simple box. Let's switch to the shape view. Reference it to Grasshopper. And I will populate this geometry with random points. Let's do it using populate geometry. And let's populate like a lot of points. Now 100, maybe it should be more. Probably like 1,000 points. Okay, this looks good. So let's say I would like to clusterize these points in terms of the walls. So I want two points that located on one wall to be grouped together. So I could select 1, 2 or 3 walls from the cube. It's actually useful for the clusterization of the point clouds. Let's say you've got some insane point cloud from which you want to select some features. Let's say wall or floor or whatever, ceiling, right? So, okay, for the clusterization, we need some parameters which we can get from these points. In this case, yeah, obviously point has 3 parameters, x, y, and z. Actually, their coordinates in the space, in the 3D space. But here we're gonna be creative and we won't use just the coordinates. We're gonna use the nearest points to each point. Let me explain it better. Okay, let's use closest points component. Make sure you use closest points, not closest point. It's important because we need to select not one, but several points. Let's say I'll go with 10 points. So for every point on the cube, we will find 10 neighbors. We can vary this number, it doesn't necessarily should be 10. It's not necessarily 10. Okay, we found these points, and I want to create bounding box around all these points. Not per object, but union box. You see there are a lot of boxes. It's good for us. And as parameters for clusterization, we're going to use properties of this actual box. Let's do it. Let's extract the parameters of the box using the construct box node. Here we have the dimensions of the box by x, y, and z axis. Let's see how it looks. Yeah, it's actually a domain. So what we need to do, we'll need to deconstruct this domain by x, by z, by y, and by z. And we have the start point of the box and the end point of the box. To evaluate the lengths, widths, and heights of the box, we should simply subtract start from the end of the each domain. And here we go. Here we have one number. This is dimension in x direction, in y direction, and in z direction. That's all we need for clusterization. I will hide this preview. And we go to our lunchbox, select Kamins clustering, and we need to provide these dimensions into the input. Let's do it by joining them with merge component, x, y, and z all together. Like this, so we have 3 items in each branch, which is good. Put it into inputs. And we'll need to provide a number of clusters. Let's say we'll start with 2 clusters. And then we will increase the number and see how it will change. Cool. As a result, Kamins clustering gives us a number of clusters for each point. You see, right? Zeros and 1. We have 2 clusters. First cluster is 0, and second cluster is 1. Let's color our points then using gradient component. We use result as a parameter. L0 is always 0 in our case, and L1, it's a maximum cluster. In our case, we have clusters 0 and cluster 1, so we have to subtract from our number of clusters 1. So I just simply use subtraction and number 1, which I subtract, and connect it to L1. Great. Let's change the gradient to something more fancy. Let's say this one is quite good. And finally, we can color our points. I will use custom preview. As the material, I use gradient, and as a geometry, I use points from populate geometry. Let's hide everything we don't want to see here. Yeah, now we don't see the difference, that because this gradient starts with red and ends with red. So this we're gonna fix by eliminating this reddish color. And now finally we can see the difference. Some points are orange and some are reds. Let's change the number of clusters and we'll see how it changed. What we have right now, we have parallel walls colored with one single color, right? Red for ceiling and floor. For walls in X direction, we have blue, and orange for the Y direction walls. That happens because our input is the same for these walls, right? So in every direction, bounding box have the same properties. In Y direction, it has wider Y and wider Z. In X direction, it has wider X and wider Z. And in Z direction, it has wider Y and wider X. That's yeah. We can fix it using additional parameters for the clustering. Right now we won't do this on this option. We'll see it on the more complex geometry. But let's try to increase even more. Like let's say 4. What's happening now? We see we've got some other cluster, right? The one on the corners. Because the boxes, bounding boxes, have different properties on the corners, right? They're more uniform. And so on. At some point, there are gonna be errors. Let's say if I increase more than 8, yeah, we've got some random points because our data for clusterization is not enough for that number of clustering. It's not different enough. Okay, I think it's pretty much clear. If you have any questions, you can write them into comments or in the chat. And we will continue with more complex example. Let's switch back to the facade. Like this, right? And let's figure out how to distinguish our triangles. So what actual data we could extract from them for the clusterization? So first data I want to extract is going to be their position on the surface. So I will find the center of each triangle using, so since it's mesh, I'm going to use face normals component to get all centers for the triangles. Once I've done this, I'd like to find the closest point on the loft, because I'm interested in the surface coordinates, UV coordinates. So I'm using surface closest point. I select my surface and then I connect centers as points. Only thing here I need to do is to reparameterize the surface input. Okay, good. I can hide the points because I don't need them. I just need these UV coordinates. UV coordinates are coordinates from 0 to 1 on the surface, if the surface was reparameterized. So I know that if I deconstruct this point, let's do it, deconstruct. I will know that X, Y, and Z coordinates are always from 0 to 1. Which is good for me because I'm gonna unitize every data I get from triangles. So if I get lengths of each edge or corners, angles, right, I'm gonna normalize all of them, because for clusterization we can get a different weight for different parameters, and to avoid this situation I want all the parameters to be equal from 0 to 1. Okay, let's continue. So we have X, Y, and Z parameters. This is good. Then what else can we extract from the triangle? The actual edge lengths, correct. Let's do it using so yeah, it's a mesh. We need to deconstruct it to get actual edges, but not like this. I think I would use mesh explode. I guess it's a plugin mesh 2000. You should install if you don't have this this node. Okay, I have all the pieces, all the triangles here. Then I will extract mesh edges. I will get their lengths like this. And as I said, I will need to unitize them. So you can use either a map, or I prefer to use normalized component from GitRaptera plugin. Like list normalizer. That's gonna be enough. Okay, next let's extract every angle. So first of all, in Grasshopper we can get angles from the actual formula. Let's use evaluate component. And this one. And there is 3 formulas for the edge length, angle values. They look like this. You can find them in Google or whatever. If you're good in math, you should know them, I guess. Let's rename our inputs to A, B, and C, and connect the lengths. Actually, it should be lengths of the lines 1, 2, and 3. Okay, now we have angles, which we in turn should normalize as well. Okay, something like this will work. There are some other data we can extract from triangle. For example, the direction of triangle, right? Let's see, the position of the sharpest angle. There are also yeah, the area of triangle. Actually, yeah, actually let's do area as well. So we're gonna use mesh area component. For this one. And also I will normalize it. Cool. And again, we can provide different weight for different parameters for clusterization. I'm doing unitizing and normalizing of data in order to multiply it later. So let's say I have a list normalizer for the edge length, and I can multiply it by some value. Let's say 1 for now. And I'm gonna do it for every parameter I have. So I will have more control on clusterization. I will define what matters more. Okay, in this case, x and y, I will multiply by the same amount. We don't have that here because like surface is flat. In UV coordinates, you don't have this third one. Amazing. Once it's done, let's merge them together. I should graft and simplify the first one. The same I will do for the second one. Then I will add the third. It's grafted already, so I just simplify. Again, next one. And the last one I should graft as well. It's flat. And simplify. Okay, at the end I'm getting how many? 9. Okay, good. 9 parameters for each triangle. This is good value. Adds a lot, actually. Let's turn off every unnecessary component. And let's use K-means clustering from Lunchbox. I will connect the inputs and define number of clusters. Okay, let's go with some like 50. Because the more complex structure you have, the more clusters you will have to do in order to approximate this structure really well. Okay, that's fine. And the thing left here to do is to color them, again using gradient. Let's select our fancy one and remove the red color at the end. Cool. Again, I subtract 1 from number of clusters connected to L1, and as a parameter I'm using results. And now let's use custom preview in order to see how our clusters are distributed. I will connect custom preview to the mesh explode, because in this way I'll be able to preview every single triangle. Can't I see it here? Something else is turned on. Okay, yeah, you can see the difference here. And if you change number of clusters, the distribution is also gonna change. Okay, good. I think we're getting it. And now let's try to change some values here, right? Where we multiplied it to give different weight for different parameters. Let's say let's decrease let's decrease the position. Let's make it 0, like it don't exist, right? And you instantly see the changes in the clustering. That means now our clusters, one cluster can be located in any part of the surface. But if we turn it on, turn the positioning on, every cluster located together. So it's like a proximity between pieces of each cluster. I suggest to keep them keep them at 1, because it's easier to assemble if you have one cluster, one group of panel in one place. But if you have them in different parts of geometry, it's going to be super messy. Okay, then let's try to reduce something else, like an area. And you can play with these values as you want until you get the best result possible. Okay, I will keep it like this for now. So, yeah, we've got all the clusters, and the thing left here to do is to change. So for now, there's still different triangles in there, right? They're all different. We just colored them in different colors, but the idea is to replace every group with one single triangle. Let's do it, right? So first of all, I need to join all the triangles together. Like every cluster should be in one single branch. I'm gonna do it in using index allocator, or allocate by index from GitHub Terra plugin. Here it is. I'll use result as an input for the index, and I use triangles for the D0 input. Something like that. Okay, so I have now 80 branches, 81 branch actually, which correspond to 81 cluster. And every branch consists of the triangles of the same cluster. Great. Now in every triangle I should create a plane. Let's do it. Yeah, we will do it using face normals. I will copy this component. It has normal and center. Let's create a plane normal. This is the origin, this is the center. Reducing the plane size to, say, 3. We'll see every triangle has their own plane. located in the triangle plane. And now I just need to rotate these planes to the sharpest corner of the triangle. Yeah, that's kind of a trick here. Okay, let's find the sharpest corner. So it's gonna be the smallest one. The smallest one here. No, actually, maybe it's better to go in a bit different way. So I will find the closest point on the triangle to the center point. Using closest point component. This is the center point, and let's find the point I'm seeking here. Vertices. Okay, I made the mistake of obviously I should graft this input, and it doesn't take time to compute. Perfect. Once we get the closest point, we shall construct a vector. Let's say a vector from 2 points, from the center to the closest point. And again, yeah, don't forget to graft things. It's actually quite important. Great. Then I align the x-axis of our new plane to this vector using align plane component. This is the plane, this is the graft. Don't forget to graft. This is the direction. And you can see now planes have been flipped, have been rotated to the right place. Perfect. Once it's done, I want to unwrap every triangle to the XY plane. Doing it using orient. Yes, I will put my triangles here. I've got a geometry. The source plane is the plane of triangles. Oh, sorry, not from here, but allocate. And here we go from allocate as well. Like this. Good. Yes, now it is correct. So we align our plane. This is the source plane. Yeah, correct. This one shift pass. Should we create here and simplify the input? Okay, good. Yeah, here we go. We create shift pass, and then as a target, it's gonna be XY. Yeah, And here in the center, in the very center of your 3D plane, you will see all the triangles packed together. Every branch is one single cluster, all together here. Let's turn off every previous preview, because we don't want to see them now. Now from the orient, I should extract all the vertices. Let's do it using the construct mesh. Turning off this. And from all these vertices, we need to construct a new triangles for every cluster. So here I'm gonna use average triangle for every cluster. So to do this, we need to use a path mapper. We need to play with that a little bit. Create a new mapping, and let's change a bit our formula here. So AI and then B at the end. It will flip our list like this, and then we find average of points and flip our list back using exactly the same path mapper. Just plug it here. Okay, let's check. Let's create a polyline. Let's create a polyline. Here they are, the average polylines. Obviously it should be closed. Yes. And now we've got 80 triangles, which correspond with 81 triangle, correct? Yeah, correct. 81 triangle, which correspond with the number of clusters. And the only thing left to do is to unwrap them back to their rightful place on our shape. And we are doing them again with orient component. But before, I would love to offset them a bit, so we don't have overlapping on the actual shape. Let's do an offset curve. Obviously, it should be negative, the value I offset. I right click on the D input of the offset curve and I write into expression -x. Yeah, and I slightly reduce the value, slightly reduce the triangles. Okay, cool. Let's unwrap them back. Using orient component. This has geometry. XY plane is gonna be the source plane, and these planes from shift path are gonna be the target. Let's see. And here you go. Now we have unitized triangles per cluster. However, we get some issues here, which we will solve by changing parameters. Let's play with parameters for a bit. Let's say I reduce the positioning. Okay, it's better now. And maybe I should increase numbers of clusters as well. Let's say make it 100. 100, yeah, that'd be 100. Obviously, the more clusters, the more correct shape you will get. Maybe also some geometry issues, but they are fixable, you see. Okay, that is great. Okay, and once it's done, it would be nice to have some infographics regarding the number of clusters, number of rectangles or triangles in every cluster, and the actual size to be seen. Let's have it. We're gonna do it using human plugin, which is quite useful, and I highly suggest to get familiar with it. We have to use render to mesh to screen to preview the triangles. Also, we'll have to use the text, render text to screen. And let's create some components which will allow us to place our stuff on the screen. So first of all, I'd love to make surface out of these polylines, offset polylines, like this. Then I place them, convert them to mesh, because we render mesh to screen, not the surface. So I'm using simple mesh. And connect it to mesh, something like this. Then we'll need to provide the location of this of these shapes, and the location is gonna be different to every screen. So we're rendering to the screen, and basically the location is number of pixels from the left bottom corner of the screen, as I remember. Okay, let's try to do it. So I'm going to use series. And also I need to have a color. I'm using index allocator again to get my colors like this. Then we'll select just a single color from every from every branch. So for every cluster, they're gonna be one single color. And let's create a grid for. So now I have 100. And we will create a grid of points on the screen for 100 clusters. So we're gonna do it with series. Let's say I know that for my screen it's gonna take from 200 pixels with 50 pixels distance and 10 rows. I'll repeat this data 100 times. Okay, this file is gonna be available for you guys. I will put a link in the description, so you can check it out and probably apply to your projects. Now let's divide our list into branches like this. Perfect, 10 by 10 right now. And XYZ, I create a point using construct point component. This goes to X. I can actually connect it already. For the location. Then for the Y, I should know the count of branches. So let's say I'm using 3 statistics and again series. And I know that the spacing here should be 110. You will play with these parameters. 280 for my screen. Okay, good. And in order to get the grid, I shall graph these points. You can see already on my screen here they are on the left. They are visible. I will tune them a bit. Yeah, I can move them up, down, reduce spacing here. Okay, good. Good. And also I should graft it here. Yeah, that's correct. Perfect. For the colors, I will apply colors from the gradient, right? And as the scale, I will measure the area of the triangle and divide it to some value. Let's say 20. And that's going to be scale. Right, so I can change the scale and make them more or less visible. Cool. Now when it's done, we should go to the text. Alright, for the text I will modify a bit our grid of points. So I will move, I will basically move these points up on the screen. So for this I will deconstruct points from construct point. I will add to the Y some value, 50, let's say. And I will construct point back. Actually, PT construct, right? Now I prefer to use X, Y, and Z to call this component. So X remains the same, Y is changed, and Z is always 0. Cool. This is the location. And the text is gonna be the length of the list. The length of the list from allocate by index. Let's say I'm using list length, moving it to the render to screen, and it is It is the text. Okay, perfect. Yeah, let's change a bit the placement. Maybe like this. And if we change the number of clusters, this will update automatically. So I would reduce a bit the size of triangles. Let's switch to the rendered view. Like this. Yeah, my mesh is black for some reason. Okay, let's do it differently. So here we have good. Here we have triangles. I will make them boundary surface and we'll color them with proper colors. This is the geometry and those are the colors. Let's hide the grasshopper. And we've got the geometry, clusterized geometry. Perfect. Again, if you have any questions, please feel free to ask us, to reach us here on YouTube via comments, or write us directly in the Instagram. Actually, please consider to subscribe and check out our cool Instagram page. I think you will love it. So thank you for watching. Thank you for watching us live, and obviously the recording is available. And yeah, see you next weekend with our usual weekend stream. I think we will continue the topic of machine learning and artificial intelligence. There is a lot to say regarding the application in Grasshopper. Yeah, see you soon. Bye.